All right, I think I am good to go. Right, cool. So I'm kind of playing around with streaming a little bit, and so like today I'm going to be doing some coding on a project I've been working on recently. So I'm I'm Ian. I'm a developer slash developer advocate at working at Google. I kind of focus on like various things like uh, software security and kind of cloud native type of stuff. I work for Google Cloud and kind of giving this a try, like doing some like kind of programming related streaming and stuff recently. So just giving this a try for now. But like basically the idea is like that I want to kind of see how this goes and if I kind of like doing it and it seems kind of valuable, then I will continue doing it on a stream or kind of regularly set up a schedule and kind of do these type of streams. So I think mostly it would be something like software development uh, type of stuff, and like I'll pick some sort of topic and then uh, kind of go from there. But like I have some ideas, like mostly. Uh, so I work on a few different projects. I have my own, a couple of my own projects, and then um, I work on some some projects around the salsa framework and security. And so some of the streams that I do might be working on those projects or working on other projects that I work on. Others might be like just like doing generic kind of lead code kind of problems or like problem like is it like those type of coding problems or coding puzzles, and then others might be like just learning a new language or whatever. I want to learn more Rust at some point, so I think that would be like one of the topics. Um, but in general, I code mostly in Python and Golang or Go, and I also code a lot in TypeScript and or JavaScript, even though I'm not a super big fan of that. But it's like one of those languages uh, that I do write a lot, and particularly with regard to things like the Salsa framework, because like that's a lot of basically GitHub actions and things like that. So today, so you can find out more about me at like ianlewis.org. That's my website. I do blogs sometimes, but I haven't really been doing that very often, and I will hopefully do that more in the future um, as I kind of start doing this more. But today, what I want to work on is like this lexparse library, which I've been playing around with. This is kind of like just an experimental library that I've been working on. If you're not familiar, there's a Rob Pike. So Rob Pike is one of the inventors of, or the lead developers on Golang or Go, and he did a talk on flexors at one point. This is a very long time ago at the Google FOSS Sydney meetup, where he talked about like the implementation of the text templates Lexer. And this has inspired a bunch of different libraries, but none of them seem to really like be kind of something that I liked, or something that anybody was maintaining with any like real like maintaining regularly. So like I wanted to work on something that would like be a little bit more stable and have like be actually kind of usable. So the idea of like Pike's implementation was that let's see if I can find a good slide here. So like basically like he has each the lexer would like parse out lexemes, which are basically tokens, and he puts them in what's called an item, and then so like he's talking about why not regular expressions, etc., etc. And so like the way that he did it was like he manages like the state, because like a lexer is like a kind of a finite state machine essentially, and so what he does is he keeps the state as a function, and so like each function will return the next state, which is another function, and basically the lexer will just go through and execute those functions over time, like in order to propagate the tokens or to like generate the tokens. So that's the kind of basic idea. And then like, so if I take a step back though, like a lexer, there is like the idea of like lexers and parsers, which is part of lexical analysis. So the idea is that like you take some text and then you parse it semantically and syntactically. So lexical tokens will be what you parse out kind of syntactically, and then semantically, like I think the parser will put it together semantically, right? So basically what you have is like the tokenizer, like if you had a language or something, right? Like the tokenizer would like parse out these individual tokens, right? Like if, like bracket, etc., right? And the lexer doesn't really like know much about the language. It kind of just parses out the individual tokens and like puts them into a stream. And then the parser, on the other hand, takes those tokens, that stream of tokens, and then forms like a parse tree of the actual language itself, right? So if you get like a C language, the C language, like you might get like this type of token, the X token, then the equals, then A, then plus, then B, etc. And then that would the parser would put that into a tree that would be like B times 2, and then the result of that, has an A attached to it. You'll have like a plus at the top, and then A will be the left side, and then the times on the right, and then B and 2 as the children. And so you get like kind of a little tree structure built out of that. And then that can be kind of like evaluated into or generated into actual like machine code or whatever you need to do with it. So that's the kind of idea, right? So you have like a lexer, and then you have also a parser, which parses into a parse tree. So the lexer produces these tokens, and then the parser creates a kind of tree structure, like, some sort of like an abstract syntax tree, so an ASM. So that's kind of the idea of this like thing. And the idea is also that we want to be able to provide really good error messages, because like when people write code, like they obviously like write code or write something that is not syntactically correct. So we want to be able to handle errors like really well. So things like, if you had like X equals A space B times 2, right? That doesn't make any sense syntactically. Like, so the lexer might not know what to do with that. Like, it'll just parse out the individual tokens, but the parser will kind of see those tokens and be like, oh, actually, this is invalid, right? And you want to be able to get good error messages out of that. So you want to know like what the line number is, what like the location in the line is, like the column number, like things like that. And then you want to give a really good explanation of what's wrong, right? So you might say like invalid identifier B, right? Like, or unexpected identifier B or something like that. So you know that like, oh, it wasn't expecting to see B here, it was expecting to see like some sort of operator, for example. Right, so that's the idea. So then, let's see. So that's basically it. Like, we have kind of like a skeleton. Like, so me and this other guy, Super Frank Chad, have been working on this a little bit. And we have a library. There's not much documentation right now, but if you look at the Go doc for it, like we have a lexer, which you can start. You can create like giving it a reader and a starting state, and the state is basically a function, right? So like here, if you look at the state is basically is a type, but has an interface, is basically an interface that has only a run method, right? So you can attach some data to the state, like if you have an implementation of the state interface, and then you have a run in. And then, so you can also, there's a state function, this is a function that just basically wraps the state type. So you can give it just a function, the run function, and it'll just wrap the state for you so that you can just like write a function and then pass it to anything that expects the state type. So you can just basically write a state in the parser that parses a particular type of token and just implement that as a function if you don't need to store any state data or anything like that. Okay, and then let's see. So this will also produce these lexemes. So the lexeme has a type which you can define. The lexeme type is just simply an int, so you can just define your own enum enumeration for this, like your own types, and then the where we at? And then the lexeme will have a value which is a string, and this is always a string because you're always parsing some sort of token from a stream, which we always know is a UTF stream. So like in our case, we give it a rune stream, a stream of runes, which is like just basically characters in Go, and this produces like lexemes, which are string values. And then we also, like, the library itself kind of automatically handles like where the position is in the stream. So like where the position is from the very beginning, what the line number is, and what the column number is. So you don't have to worry about that too much in terms of like, and this is as you're parsing, you don't have to do any of handling of that. And also, like, you can just use these positions when you're creating error messages and whatnot. So this is really useful because this like goes straight to the parser, and then the parser can use that information if it needs to generate error messages, etc. Right. So we've got that, and then so this lexer basically has a bunch of ways of interacting with it. And basically what happens is the state functions that you implement will take a context, and they take the lexer itself. And then the lexer will allow you to do things like advance a certain number of characters, or like get the current column, get the current, like discard some number of values, right? And it keeps track of the current kind of lexeme position, right? So the current position in the stream. So that's why there's like an advance versus discard, right? So it keeps track of like where the lexeme position is, and discard will just advance the current position, right? Whereas, it basically discards and moves the lexeme position, so it basically just throws away all of the number of characters that you specify. Whereas advance will not advance the lexeme position; it just advances the stream. And so then when you actually emit a lexeme, it knows like that this is the stream, or this is the characters that I need to emit at the lexeme, and then it can like advance, if that makes sense. So like basically, so you have this stream going on where the individual position of what you're processing and the location in the stream kind of goes and like keeps moving, and so you'll like move along and then emit a lexeme, move along, maybe discard some characters, move along, emit a lexeme, and then like keep going along as you're parsing the input. And then the lexeme can or the lexer can allow you to emit a lexeme that you define here, but you also, it provides this lexeme function which you give it a type, and it basically generates a new lexeme object at the current position. So there's an example here of a very basic template language, right? So here's an example of template language. So if I jump to the bottom here, there's a lexparse function which will take the stream. So in this case, we just have like a hello subject template that we give to our lexparse, which parses the template. And we give it a state text as its starting point and a parse init as the initial parsing location. And like, I should step back and say that the parser works very similarly to the lexer in the way that it like works, but it's operating on a tree rather than like a stream of, or like just emitting a stream of lexemes. It actually, like, you build up a tree with the parser. So it works in a very similar manner. So we'll kind of see what that looks like in a second. So like then so what this does is it runs lexparse, which basically creates a lexer, creates a parser, and then like, wires them together, and then runs the lexer and the parser together, and then you get back a tree, a parse tree at the end, right? And so like this tree, you can then, in this case, you pass the tree to execute, which you give it like some data. So basically just like any other templating language, you give it an execute, and this tree structure represents the template, and you call it and tell it to execute, and you give it some data. In this case, the subject is world. And so once it executes the template, it'll replace these values of the data into the template and return the text. So you get hello world. So it's really simple, but the implementation is a little bit more complex. So you get like, the idea is you start out like seeing some text. So here's the parse init. So we'll go up to the text. So state text is just parsing normal text. So this text just gets output normally in the output stream, right? So you get like that hello portion, which is not an actual action, just gets output as is, right? So this is just going to create like a text type lexeme, which is, and the value is just the bare text, right? And so then when you go here and you say like progress to the, as you're doing this, like you're kind of like advancing, and then you're looking for these brackets that say like this is a variable in your template. And if you find one, then you can kind of change the state to the action state, which is like one of those brackets. And then as you're done, you just pass it to the next state. Or if the state is nil, then that gives it, the lexer, like an indication that the lexing is done. Right? And so like when it hits like one of those brackets, you get like you pass it over to the state action, which then like gets executed, and this will parse the actual brackets. And so you'll start with the double brackets in the starting, and then you'll look for the ending brackets. So you'll discard, here we just discard the brackets at the beginning, then we go look for the right brackets, and once we found them, then we basically take anything in between and we parse that as a action token. So this is going to do that, and then it just discards the right brackets and then goes back to parsing text. Right, so it's pretty simple, the idea here. The code is a little bit, like, looks a little bit verbose, but like some of the things like finding the right brackets, for example, there's a lot of this, there's some methods like find here, which will look for specific types of tokens that you expect next. And then return you the token that was found, and kind of advance the reader such that you can output a lexeme for the values that you found. right? So here we go, like down here, we create a lexeme, and then we omit the lexeme if it's not empty, right? And then on the parser side, the parser is going to take the individual lexemes and go through them and create a tree. And so here, the parse init starts the parsing process. It pulls the next lexeme off the list, and then based on the type, it creates just a simple like a simple parse action or parse text node in the tree. And this is just a very flat tree, right? So it's just essentially a list of nodes attached to a root node. So it doesn't actually really form a tree structure in this case, but for more complex languages, you can imagine a tree structure. And then here we parse the text, parse normal text nodes, which then says like, okay, get the lexeme, and then generate a text node, and then go back to parse init, which will kind of start this process over again. And then action is the kind of brackets, like var variable, and that's going to take the next lexeme and just emit an action node, and gives you the name of the variable here in the action as part of the node. So that like when you actually execute this thing, you can say like whenever you hit an action node, you can replace it with the right data value that you're given. And then execute basically just goes through all of the nodes, and writes the text nodes as is, and then the action nodes it just replaces with the value of the data that was given by the user, right? So pretty simple. And so that allows you to parse this into a tree, which would basically be like a text node, then an action node, and then another text node. And so when the execute goes to run it, it says it encounters the text node, it outputs that as is. It encounters the action node, which is called subject, and it goes, okay, I need to replace that with the data, which is the subject to data here, which reports this with word, and then it moves on to the last text node, which is this exclamation point, and it outputs that as is, and so you get hello world in the output. Yeah, pretty simple stuff. But you can do like much more complex stuff with this. One of the things I'm working on is like making like a calculator, so that you can write basically some algebraic expressions and then have it parse it and execute the find the output, or execute the input and find some output. And you can imagine that like you could do that with in a very template style. Like you could have variables like x and y and things like that, and then like based on what sort of variable values you're given, you could replace those values, or it could even do some algebraic like simplification or things like that as well. So that's kind of what I'm playing with. All right, so like if I go back to this, one of the things that I'm playing with right now is I want to create this like algebraic interpreter. So like what I'm doing is basically I want to be able to take these type of expressions and like parse them into a parse tree and then be able to execute them. And I want to create like an example code that does this, and then have it be kind of a Golang testable example. So what that means is that example that we just saw, right, this lex parse thing, this is like a full testable example, right? So like you can say at the very end here, I actually have a main function, right? And then in the code for this, there's a comment that says what the output is, or the output should be, and that basically that should then when you run tests or whatever, it will actually execute this main function and check the output against what's expected, as like a normal test, right? So if I go to the actual code for this, this example test. That is the, you'll see here in the output, there's an output comment here, which tells you what the output should be. And so like the normal testing framework can actually run this and then check to make sure that the output is the expected output. Right, and it's also documentation because like this is an example, some example code that people can use to understand how to learn the library. Yeah, so the idea is like I want to make another testable example that does that instead of being a template library is basically is an algebraic interpreter. So, and it also implements order of operations and all of that stuff. All right, so I have like a partially implemented version of this, which is an infix notation calculator. And if we look at the code for this, it's a good deal of code, but there's some things that need to be fixed up. So we have some linter errors, we have some other stuff, and I believe that this actually doesn't even run properly. So we can kind of go through the code a little bit and see where we're at, and then try to fix this up. Right, so like there's some, one thing is that like I have to rename the example test to like a new file name, and I'm going to create like, so in this case it's the template example, and then this one's going to be the calculator example test, and then we also have made a small change to the lexer to add this value method. So let's take a look at the code in the, so I might be switching around a little bit. So I have like two, this is a Tux terminal. So I have two different terminals open at once, which I can switch back and forth from. And you can kind of see that like here down in the 1 and 2, these two different terminals, which I'll switch back and forth to. The second one I'm going to use mostly is going to be my editor, and then the first one is just going to be my CLI. I kind of do it that way, so it may be a little bit difficult to look at, and I may start doing things like running terminals inside the editor itself a little later, but I'm not super used to that right now, so that's when I'm gonna go with what I usually do. So this one, we have calc example is the name of my branch that I'm using. Let's see if it's here. If I look at this, this should be just the add prefix calculator example, and I have the one commit for now. And I'll probably just update that commit and force push it, no big deal. So let's look at the calc example test. All right, so this is going to like start up the I'm using Vim Go, so that's like in the background it started up the Go related stuff. So here what we have is like we have this parser and the lexer states functions. So in this case what we're going to do is like just the state expression is kind of our starting point, and that's going to kind of continue to go on and look for the individual operators and things like that as part of our language, expression language. So in this case, like we're looking for like open parentheses, close parentheses, like plus, minus, asterisk, and like slash for our kind of operators, and then space and tabs are our white space. And in this case, we're basically just discarding those because they're not meaningful. But we do like kind of emit, or we do like kind of parse individual things like close, open parentheses and close parentheses, etc. Right, and here we're just checking to see if it's a digit by looking at the actual character numbers, and then parsing individual numbers here. Right now we don't have any kind of support for for variables or anything like that. So then we have like parsing numbers. So this is going to parse looking for individual digits until we find one that's not a character that we don't expect, and we kind of expect that that's where the digit is. But we do have to parse like floating point numbers. So if there's a dot in there, we have to be able to parse like 1.2.1.2345 or something like that. And so this will look for that, but we eventually will have to kind of check to make sure that the number is well formed, right? Like, so we don't have like 1.2.3.4 or something like that. Like that doesn't really make any sense for our like expression language. Like, that's not a valid number, right? Like that's like a version number, but that's not a valid number for this purpose. Right, so right now what we do is we check for the peak, we look for the next room or the next character, we check what type of character it is. If it is like not what we expect, then we'll kind of like expect that we've gotten to a point where all the numbers have been processed, and we'll just emit what we've seen so far. Otherwise, we will continue to advance because we know it's a number. So we'll keep advancing as long as it's a number or a dot, and then when it gets to something that's not a dot, like a white space character or an operator or something like that, then we'll actually like stop and emit all the characters that we've seen so far. So for open parentheses, we're going to do kind of a similar thing, but we only have to like parse one character, right? So we're going to, once we get to the open parentheses state, we know that we've hit a parentheses, so we'll just advance one character and emit a parentheses type. Same with close parentheses. Operators are also similar because we don't have multi-character operators, we just have single character operators, so we just advance one character and emit that type. And then that's basically the parser. That's the lexer, sorry. The parser does a similar thing, but it's actually going to create a tree. It's going to take all of the lexemes or the items that it got from the lexer, and it's going to generate a tree based on the order of operations. So I believe this is where it's not completely well done. Like, or I'm not completely finished, and like there's kind of issues left. So here, basically what we have is we have a node type, or the node types. So here we're defining a number, parentheses, or an operator node type. And then, so the operators are going to have children, and those children will be like the left and right side of those operations, if that makes sense. So the number values will have just the number. The operator values will just have the operator itself. In this case, it's just a single character. And then the node value itself, node values will be, these have their own kind of like type. So, or the node values are basically a conglomeration of the two different types. So like each node in the tree will have a node value as its value, and depending on the type, this node type that's set up here will have values, the actual values in the num value or num val fields or the oper value fields. So basically what this does is it's extending this num and oper val. So like you'll have a node val, and then that will have an oper and a num field. So all the fields from num val and all the fields in oper val from oper val are kind of filled into the node value here. That's kind of the way of extending structures or extending types in Golang. And so here we have a string, so we can provide some debugging and string representations of the node types. Parse expression basically is just the starting point for our parsing. And then this is going to basically, based on the type, it's going to go to each, we're going to return each individual parsing function. Parse num is going to parse a number, and what this has to do is it's going to get to a number, and that number, we're going to expect that there's something before it that number can be applied to, or that number is at the beginning of the expression, right? So it's either the left side or the right side of an expression, right? So we have to have like 5. 5 by itself would be like kind of a normal expression that just evaluates the 5, or you could have like 5 plus 6, right? So like, and in that case, you would end up with a tree that has like plus as the root, and then 2 children that's like 5 and 6. So in this case, we get to a number, we're expecting that either this is like starting the stream of lexemes, so there's like, so it can either be the root node, or it's got to be added to some other already existing node that we've already seen before, right? So like if we get to here, we're going to check the current position to make sure that we're like, it's either the beginning, so the current value is nil, or the current place in the tree that we're at, like the last value that we've seen is an operation node type or a parentheses, right? So we expect that we're like at the beginning of like kind of an operation, or we are like we've just seen an operator. And if not, we're going to return that like we found an unexpected number at a particular position. And then like here we're going to like parse the float value, and if we get incorrect parsing, we'll return error there, and then otherwise we'll generate the number and push it as a child of the current node, right? So if we're starting, like if we're at the very beginning of the expression, we're going to add this to the root node, or as the root node, and then we're going to, if not, we're going to like add it to an existing operator node or parentheses node that is going to right, so it's going to act as it's going to be pushed on as a child of the node that's currently active. And then let's see, we also have like parentheses nodes. So these are ones that like kind of in the order of operations kind of tells you that these have to be evaluated first. So that like when we actually evaluate this expression at the end, we know that the parentheses have to be done first. And so like all the children of this will be have to be evaluated first before the parentheses node can be evaluated, right? So like this is going to go on as its own kind of node type, which just indicates that it needs to be evaluated first. And then, so this like basically adds a new parentheses node, and then the close parentheses, when we hit a close parentheses, we've got to walk the current node. So like what we're going to do is we're going to hit an open parentheses, then we're going to kind of parse everything, all the other stuff that's inside the parentheses, and those are that'll go as children of the parentheses node. And then when we hit a close parentheses, we're going to be like somewhere below the parentheses node, and so what we're going to do is like just walk up the tree until we get back to the parentheses node, so that we can kind of continue building the tree out. So what we're doing, like kind of as we do this, is we're like building a tree. So like we'll get some new tokens, like, and then based on those tokens, we're going to build a tree, and we've got a current position inside the tree, and then like, so we might move our position inside the tree, add nodes to the current position, things like that. So we're kind of like building out this tree as we're going along. So in this case, what we're doing is that we have the closed parentheses. We don't actually alter the tree. We just alter where pointing to inside the tree. So we go back up to the parent parentheses node so that we can kind of continue going on. So here what we do is we say, like, we check to make sure that we're in a position that's sane, right? So we do a sanity check here and provide an error message. Otherwise, we go back up the tree to find the parent parentheses node. And then, so we go down here. So we say for pop the tree node. So pop means basically get the current node and then move up to the parent. And so what we're going to do is we're going to find the parentheses node at the beginning and go to its parent at the end. So here we're just kind of popping up the tree. And then if we find the root node, we have an unopened parentheses. So we might hit a case where we just hit a closed parentheses with no open parentheses. And in that case, we want to be able to say like that this is like an unopened or we expected like an open parentheses, so we have an unexpected closed parentheses. So we'll emit an error here and give the position, and then then we'll look for the parent or the paren nodes type, which is parentheses. And if we found it, we just break out of the loop and return. Right, and we go back to parsing the expression. So here we're going to parse the operators. So this takes the next lexeme, checks the current position to make sure that we're in a position that's sane, and then we're going to also check to make sure that we have to check that that we're not at the root node, right? Because like we can't do anything if we're hitting a operator first in the expression. So we might have something like times 2.5, right? Like this would be invalid because we don't have a left-hand side of this. So with that, we check that, and then we also check to make sure that we're not like doing something like duplicating it, having multiple operators in a row or that sort of thing. And then after we've done that check, we have to we get the operator value, and then we push that as an operator node. And what that's going to do is that's going to add the node to the current node. So we might hit like, we have like, say we have a value like 1.5 times 6.0, right? This is our kind of expression. Oops. What this is going to do is it's going to say like, we're going to have 1.5 like kind of on the tree already. And then we've hit the operator, we're hitting the operator here. And what this is going to do is it's going to push the operator as the child of the node temporarily, of the 1.5 node temporarily. And then we're going to do this like rotate left operation, which will then rotate the tree like this, the nodes like this, such that the operator node then becomes the parent of its previous parent, right? So like we're going to go like this, and the 1.5 is going to become the child of the operator. And then we're going to be pointing at the operator at the end of that operation, so that when we hit the 6 next time, the 6.0 as the next token, that then just gets added as the next node of the asterisk operator, right? So it's like kind of you have 1.5, then you add the operator node, rotate, and then the 6 goes on the end. So then you have as a result a operator node, and then the two nodes, the left and right hand side of the expression, right? And then multiplication and division need to happen first. So if the parent operators are one of these, rotate again. And then So this is going to make sure that we are going to always do the operator, the times and the slash operators first, right? So like if you have like a plus, you have something like, let's delete that. Now if we have something like 1.5 plus 3 times 2, something like that, right? We want to make sure that 3 times 2 is evaluated first, and then the plus happens, right? So we get like a tree that looks like, you know, plus, and then the children will be 1.5 and times, and then on the time side we'll have 3 and 2, right? So like this will get evaluated, and then the result of that will get added to 1.5, right? So you have a tree something like this, where 3 times 2 is evaluated first, right? So like if we start like, then if it's like this, then that makes sense. It'll get to that form naturally. But if we have it like this, where the plus is at the end, right, we might start out with 3.2, right, 3 times 2, right, and then we add the 2, the plus, and what we don't want to do is put the plus, actually, I think 1.5 plus 3.2, I think this way is the way that's wrong, right? So if it's at the end, it will happen naturally, but if it's at the beginning, you'll have 1.5 with a plus, and then you'll hit 3, right? So you'll have 1.5 plus 3, and then you hit a times, and that will get replaced in here with 3 and 2, and so that'll kind of work. And so actually, like, offhand, I'm not sure exactly why we need to like rotate this again. So like if it's an operator, does you want this to be like this? I think it's one or the other that's like, that's wrong, right? If you get 1.5, if you get 3 times 2 first, yeah, maybe it's 3 times 2 first. Oops. I'm not used to doing this on Windows, but let's see. If we do 3 times 2 first, and then we add, do this 1.5, we'll have 3 and 2, and then when it hits the plus, that will like, by default we put like the plus here, come on, and then put the 2 and the 1.5 below it. Right, so you'll have something like this, where this times would get evaluated second, right? So this plus would happen first. And so what we have to do is we have to rotate, like when the 1.5 gets put on, we get like rotate left, the first rotate left, then we end up pointing at the plus here, and then we have to rotate again if our parent is if this parent is like a times or divide. So that would result in the that would result in 3 times 2, or 3 times, or let's see, the plus 2.5 first. I really don't understand this. Not really that used to this cursor, because normally when I'm using this, like, it'll show me like whether I'm inserting or not on the cursor. But now I have to like look at the bottom of the screen in order to figure out whether I'm on insert mode or not. Okay, so then that's going to put my 2.5 here, and then, but I think it's not going to be like another rotate operation. It's going to have to be, it'll be like a 3.2 what am I doing? So the plus and then the 2, so it ends up like, it will end up like, like this, with the 3 and the 2 over here, right? So it's like the plus with 2 children, the times and the 1.5, and then 3 and 2 on this side. So it'll kind of like rotate the, rotate it again. But I think that this is like actually incorrect, because what would happen is you'd get 3 like a times at the beginning with 3 and plus 2 and 1.5 here, and we want to rotate it and make it be like this, but that's not going to necessarily rotate properly. I guess like that would rotate right with, so like I can't remember exactly what the rotate left operation will do, but I think that might be right, like where 2 kind of gets rotated around. So these 2 parents like get rotated, and the 2 goes to the child here, and the plus gets promoted to the parent. And this is kind of a normal-ish operation, like in a binary tree, right? Like, so, right, so if you look at tree rotation in binary trees, you know, you get this kind of an operation, right? So like this is exactly what we were just talking about. So in this situation, right, with the 3 times 2 plus 1.5, what we want to do is rotate it around, and this beta here is like our 2 here. It's going to go from being a child of B to being a child of A, and then B gets promoted to the parent, right? So like this is a pretty classic rotation, or like a classic thing that you do in binary trees. Not so much in like n-ary trees where you have like multiple children, like you don't see that too often, but that's basically what we're going to be doing. Like in our case, we just have arbitrary number of children, and what happens is when you do the rotation, that we're going to like rotate a single value and keep all of the other values kind of in the same order, right? So we're going to like append it to the end and like move stuff around. So like we have an issue, I think, currently where this rotate does not do what we would expect. So with n-ary trees, it's like a little bit goofy, right? So right now, what's happening is that you have a plus 1, a2, like we have this kind of a situation where A1 and A2 are the children of A, and then we have A2-1 and A2-2 are children of A2. And then after it rotates, we get this kind of a situation where we have the children of that were the children of A2, they're just sitting there on A2, and then A gets moved around as a child of A2. So we end up in a situation like this, whereas I would expect this to happen instead, right, where the existing ones stay where they are. But I think that like that's actually not even correct either, right? Because with tree rotation, you expect this beta one to not stick onto beta or stick onto B, right? You would expect that that the left value becomes a child of A, right? So this A2 sub 1 would actually become a child of A, and a sibling of A1. And this is actually something that's like really ill-defined with n-ary trees. So it's kind of, it may be difficult to reason about like what this should actually do for an n-ary tree. I think there's something going on with these diagrams, but plus unsupported markdown list. Okay. Yeah, I think these need to be like strings or something when you. Yeah, I think what we're trying to do is basically do this kind of binary tree rotation, but the problem is that for an n-ary tree, it's kind of ill-defined, like which values should swap over to A, right? Whereas in this case, like in the case of a binary tree, you know, like a left and right operation, or the left and right are defined, right? It's as the children, whereas in an n-ary tree, you could have any number of children, and so it's like ambiguous which children would swap parent. So I think that's the main difficulty with implementing this the way that we've got it. In the case of this particular infix calculator example, we just have basically binary trees. So like doing a rotate left operation would be normal. Would be like the kind of normal rotation, binary tree rotation. But I'm not sure if what we would do in a general case. I wonder if there's like an n-ary tree lead code, rotation, like any kind of n-ary tree rotation algorithms that are kind of standard. N-ary tree data structure. Convert an n-ary tree to a binary tree. First, we'll link the immediately children nodes of the given parent node together and form a linked list, then we'll keep the link from the parent to the first child and remove all other links to the rest of the children. Repeat the process and all children process the internal and rotate the tree 45-degree clockwise. The tree obtains binary tree representation of a given n-ary tree. Okay, so like here we're doing like creating a binary tree representation of an n-ary tree. Interesting. n-ary tree node and binary tree node. Solution B tree encode n-ary tree, and like so doing is taking that row left. So he's getting the left value, and then the right value is going to be the child, in particular child, and it's going to like just encode like downwards all the rest of the same character nodes down the right side. So the left value is the first child, and then all the right values are going to be it's just going to get right, gets the first one, calls encode on it. Okay. And then cur equals cur right. Okay, so it's going to call encode on the right side, and then convert it to add it to like make the right side the current value. Interesting. So basically encodes the left and encodes the right. Okay. But it's interesting that it's like, it's kind of doing a recursive algorithm to the right side. Or like, in this case, it's just calling encode on the left side. I mean, it's recursive here as well, because you're recursing through all the children of the left side. But the left side is the first value of the n-ary tree, and then the right side is just a, like, I feel like the rest, like if you have 5 child nodes, the rest of the 5 child nodes are just going to be like concatenated or like expanded out on the right side here. So we get like a parent, the first node is on the left, the second node will be on the left of the next child, and then the third node will be on the left of the right child, like it'll just be like this long tree with all of the nodes, the n-ary children nodes, as the left values. So one solution would be to convert the n-ary tree node into a binary tree node in a similar fashion, and then do the rotation on that. But this is kind of like a one-way expansion. There's not really, as far as I can tell, you can't go back the other direction. Like this is a lossy conversion. Yeah, like I'm not sure that like an n-ary tree like rotating n-ary trees. Like, so this is a similar question. Given challenge that inverting a well-designed binary tree, and explain a bit. Given an n-ary tree with the following structure, tree inversion of the tree is possible to navigate the children of each node, which is treated like a loop, and formulate tree operations. Rotation use only 2 properties need to be added: offset 0, default, and default is represented plus 2 properties confining. Yeah, I'm not sure this really helps. I don't think this really helps either. So like, maybe what we can do is just like, we don't really need to have the rotate left. We can just have the rotate left be not something that's built into the parser itself, but it's just special case of that it's only that is implemented by that particular parser. So like we don't have to have this be part of the library itself. It can just be part of the example. So I think what we want to do is just remove this from the library itself, and then have the example have its own rotate left, and that rotate left will do it in a binary tree style. Right, so we'll implement this thing as a rotate left, but this rotate left will be like just a rotate left, kind of like this. It's not part of the that's not part of the actual parsing library. Okay. So how do we rotate left? We'll have to do something like that. So let's look at take P, which is the parser. P. Why is that like? I don't understand that. P. There we go. So rotate left is going to take the parser, which includes all the tree and everything, and so we're going to like implement the rotate left. So what happens is we take the current what we're going to do is take the current value B, and I think we're going to start at B. Yeah, so like B is going to be like kind of the current location, right? And we're going to take the left value, give it to its parent, and then rotate the two, right? So there's basically two values that need to happen, or like two values that need to change three values. So the left side of B needs to change. The parent of this beta needs to change, the left side of B. And then the child of B needs to be replaced with A. Like beta needs the beta location, the left side of B needs to be replaced with A. And A's parent needs to be updated to B. Right? So we need to parent of B so we need to set parent of B to parent of A, set parent of A to B, set parent of beta to A, set left child of B to A, and also set right child of A to beta. So like, come on. Right. lex parser node val because this is a generic using generics types. Using generics. Something I'm not used to, like, is like pressing backspace. I think I expect that it's gonna like change it to like the or to be in the insert mode and then hitting backspace. But it's not. Okay. So basically, this is kind of the order of the operations that we need to do. I'm not sure if this is the exact order of operations because we might lose some value at some point, but so current node is p.pause. So this is the position. So my parser, I have a pause here that's going to give me the current position in the tree, and we're going to take that to be this beta node because we're going to be rotating about beta. So well, I guess technically this operation, if you're doing rotate left, it would be on this 17 node. Like the operation is technically on the 17 node, which rotates it down instead of rotating 50. I guess it assumes like the root of the rotation is the current node. So like, I guess we'll assume the current rotation root is like the current position, and then so this is basically going to be this is going to be A, right? So root will be essentially A. And then we're going to like say set A's parent. So root parent equals so root C let it parse. Let's see. I want to look at the type, node type. Right, so over here we're going to see like we've got parent, we've got children, we've got value, which is V, and then we've got position line and column. Okay. So if we go back to this here, root parent is going to be set parent of B to parent of A. So the first thing we're going to do is we're going to change A's parent to B, right? So children step 1, right? So we have a left child, and okay, so root, we have the right and the left. This is left, this is right. Come on, for real. So I'm changing my mode here. And then parent, and then let's see. So we want to say the right parent, if we're rotating left, like the right side becomes the parent. So this is B. This is alpha, I believe. So we'll probably not need to do anything with alpha. And then, so root.parent, right? So we're going to move the parent to the right. Set parent of A to B. Set parent of B to parent of A. So 50 becomes that. So this root, this 17, like this root, the root's value becomes that of its right, becomes the right value. So we need to save the previous parent. And then we need to say like root.parent equals right, and right.parent equals parent. Right, so we're going to swap the parents of these. And then set parent of B to parent of A. I'll do that first, and then set parent of B to A. Set parent of A to B. And setting the parent of beta to A. Beta is our right value. Let's just call it beta. Is going to be the left side of B. Right, so right dot children 0. And the right side of that is like, this is theta, right? So theta is right dot children sub 1, right? Okay, so these might not actually exist, but we'll have to do those checks later. Set parent of beta to A, so beta dot parent equals A. A is the root value. Set left child of B to A, so B is our right value. Children sub 0 equals A, which is root, and then set right child of A to beta, so root dot children sub 1 equals beta, and beta is beta. Okay, so we have something like this, right? And we don't actually need to use alpha, as we said before. And theta also remains the same. Right, so that makes sense. So right, this will perform the rotation. For us, I believe. What we want to do is we want to say like, we need to make sure that we are doing this correctly, even if those values don't exist, even if they're nil or the children don't exist. So, basically, like if beta doesn't exist, let's see, if A doesn't, or if B doesn't exist, this doesn't really make any sense, does it? Right, so like if we run rotate left on the on A, and there's no right side of A, then this doesn't really do anything. Right, so like we'll say if when root children is less than 2, So like, root, and this is right. It's like you can't really do a rotation on this A if B doesn't exist. Right? If it's just A and the left side of A, or A is a leaf node or something, then rotating it doesn't do anything. Right? So then we say like that. So we know that the children, there's both a left and a right side of, we know there's at least a right side of alpha, right? Or there's a right side of the root node, which is A. And then, let's see, beta may not exist, right? So we want to say like, if let's see, right children is greater than 0. And let's see. We'll set this parent. We'll update the beta, and then right's parent and root's parent get updated. Left child of B becomes A, and right child of A becomes beta. Okay. So we know there's at least 2 children of root, so we know that this is going to be a valid operation at the end here. This children 1 equals beta. But we don't know how many children that right has. Right children is greater than 0. Okay, so here we have to say like, we check to make sure that the children right is greater than 0. If so, then we take the right side and we update its parent and we update its children. So we can say beta dot children or beta. Actually, that's wrong. We do need to update right children. 0, the 0th value of right children equals root. Okay, that makes sense. And then we know this should be always correct. And root parent equals right, and right child of A to beta. Right. Okay. So I think this is correct, right? So if we need to make sure that the right side of the root has at least 1 child, which is going to be the right side. It'll leave all of the other ones in place, but we're assuming that with this rotation that we only have two children anyway, but we need to make sure like the left one will be the first child and the right, or the left one will be the first child and the right one will be the second child. And so we make sure that we have at least more than 0 children to make sure that there's a left child. Okay. All right. All right, so like I think that's basically a good implementation of that. I think I want to use some names other than beta and so let's say left of right is beta. And then right children equals sub-0 equals root. I feel like this is going to be wrong, right? Like, no, that's right. Yeah, I just like straight up overwrite it. I don't need to like shift any of the children around. Like I can just update the existing values. Right, and then data is going to be left of right. Right child of A to beta. So like this also only happens if there is a child there. Okay. Then I need to update these. And then set parent of the root to the right child. Okay, so let's remove beta set parent of the to root node and child of right node roots right node to root and set the right child of root node to the left child of the right node. Okay. Okay. All right, so this is like, should work as our rotate left operation. Right? And then the other thing we need to do is set the current node. New root node. So this has to set the current node. And I believe there's not really a way for us to update the current node. The current node is still of, as far as the parser is concerned, is the current root node. So in this case, it's A, right? Like, so this is where the current node is pointing to. After we've done the rotation, we want it to point to B, right? So after it's been updated, what we can do is we can just tell it to move to its parent node. So p.climb. So climb will update itself to the parent node, I believe. It has no method climb. Maybe I don't have like that. Is that on a pull request? I thought that I had that. I thought that existed. Yeah, there is a climb method. Huh. Okay, so let's go ahead, and what I need to do is I don't think I have the latest version of main here. So what I need to do is I'm just going to go ahead and commit, add everything. Just arranging existing commits. Okay, that's it. Then check out main, pull main. Yeah, it says it's already up to date, so I think what's happened is I have main already, but I need to pick out the calc example main to base this on main. Okay. And then that should allow me to have climb. So it's changed. All right. So here we've updated this main, so like there's no longer a tree anymore. This is just a node. And we have some other sort of problem here. Pop. Pop is undefined. So I think I renamed pop to something else. Push. Place. Rotate. Dot sibling. Did I remove pop completely? Okay, it's possible that I removed the pop method. So did I remove that? And what did I do with it? Okay, so I removed pop. I see, it's just called climb now. So it just goes to like okay. I guess like we do have push and pop, but like pop I guess I expect to like remove a node from the tree, whereas climb just climbs up the tree. So I think that's why I changed the name. Because pop would kind of imply that you're removing something from the tree and then moving up to the parent. So I may re-add pop back to the library, but for now it's gone. Okay, so we have that. Where is the other error here? I see. So t.age, this just returns a node now. So we just say print node and now. Okay. So this should kind of work. We've done the rotation part now. So if we say like, so I have this set up so that we can run make to do a lot of the various tasks. So this is going to like run the unit tests. Like in the make file, we have this like little script here that will run go test to actually test the to run the tests, and then output a little coverage file and check for rate conditions and some other options. This also sets a timeout by default, which I think I've changed it down to like 10 minutes. I can't remember what this is by default. I think it's like 5 minutes, but I've changed it to 10 minutes for whatever reason. Probably because of so that it runs the pre-submits work properly. So if I run this, it should execute our example. And it failed, which I kind of expect. Unexpected operator / at position 19. Okay. Okay, so this is like maybe done in such a way that I don't expect it to, it shouldn't expect to work. Or, no, it kind of looks like it should work. Like this parentheses and this parentheses thing should still work. Let's see if it works in this example. No. So some other kind of bug is happening here. It's getting to this point here and failing. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, yeah. So it's getting to this point and it's failing because it's not expecting that. I'm not sure why. It says unexpected operator at position, whatever. So it's one of these two errors here. And it should tell me exactly what. So calc example address 352. So 352 is here. So that's actually the error. So I'm not sure which one it is. So we could return all that value. Unexpected operator position, blah, blah, blah. Okay, so this is likely not the problem. resolve this for the fun. We should not see that if we run this again. Yes, it's not in the error. So it's definitely this one. So if the current value type is operator node and then the current children has been less than 2, then do whatever. Okay, so I think what happens is, like, we're not expecting, when we do the rotation, we're not expecting to be at a particular position. We're expecting to be at a different position in the tree, and so that's why it's happening like this. So multiplication division need to happen first. So parse operator, right? So like we want to be at the operator node. So we are parsing along, we get to an operator, and the right side doesn't actually exist yet. So like this B, we'll get to the operator, we'll get to an operator here, right? And we add it as a child of the left node and then do rotate left, right? So like, let's imagine we're at like 1.5. Okay, let's actually like take a look at what we would get with the example that we got here. So I don't have like a way of drawing here, which I should probably have. For crying out loud. Really? I don't have things installed on this thing. Oh, there we go. Can I make this like dark? Let me just fill it with black. Okay. And then here. Okay. And then white color. Why can't I draw like white on this black color? I don't understand that. Okay, there we go. Strange. Okay, so we're gonna like, let's put this over on the side here so we can see the example. All right, so we're gonna start out, we're gonna have like 15, jeez, I can't like write with the mouse for shit. 15.2, right, we'll hit it times will go here, and then that's going to rotate, right? We're going to say so let's actually I need to get better at using paint and things like that. So we'll have like 15.2 good lord, times 1.8 plus 7.9. I need like to get a tablet or something like that so I can write here. Oops. Minus 2.5 divided by 3.0. Right, and then if we go over to the code here, right, if we say like operator, first operator, right, like this is going to say right, so we'll start out with like 15.2, oops, 15.2, damn, that's bad. Then it'll like get a star, and we'll push that on as a star, and then we rotate left, right? So like we're currently pointing here, and what it really should be is pointing to here when we rotate left. So I think that's like one of the issues, right? Because like rotate left is going to assume that we're at here, and so when you do rotate left, it's not actually going to rotate left. It's going to be a no-op and do nothing. So I think that's the first problem. So push, instead of push, right, push is going to add the node as a child and then update the current node to the new node, to the pushed node that's been pushed on, right? So that's going to like push on this operator, and then it's going to update the current node to this one, right? So what we don't want to do that. We don't want to actually do that, right? Let me just do this, and then I can do that. What's that? So instead of doing that, we're going to just say like node is going to like creates a new node in the current lexing position and adds it as a child to the current node, right? So like what we're going to do is we're going to say so here instead of push, we're going to just say node, which adds a current node to the current, adds a child to the current node. So it's going to just stay here, and like, I wish I could do, like, just make the background black. That would be much easier. So yeah, it's going to stay here, and it's just going to add a child, right? So that's the first thing. And then when we do rotate left, that should work properly, right? And then if the operator that we added is a multiplication or division operator, we need to rotate right, or to rotate left again. Let's just take this out for now. Yeah, let's take this out for now and see if this runs. No, it doesn't. Unexpected parentheses at position 7. Let's print the operator, and we'll do like print node. I don't think I can look right. I think something like that would work. Maybe something T. Right, okay. Let's see if that like gives me some debugging. No. I didn't even get there. Okay. Did it print an operator at all? No. I'm only getting to position 7, so like 1, 2, 3, 4, 5, 6, 7, like this 7th character. 5, 6, 7. Oh, let's see, it's times 1, 2, 3, 4, 5, 6, 7. So at position 7. This is really position 8, I guess. 1, 2, 3, 4, 5, 6, 7. It's position 8, really. I should update that. Yeah. So unexpected parentheses at position 7 says that yeah, snail or the value type is not a number type. this is kind of wrong, right? This should be like if it is a num node type. So like I don't want to support like just having a number like 3, 2 plus 5, right? Like the way I'm doing it is like you have to have the times operator here. But this is checking to say like if the current value is nil, i.e. you're in the middle, you're at current value equals nil would mean that you're at the root node, I think. Or you're at, the type is not equal to a num node. Okay, actually this is the closed parentheses. I want open parentheses, right? So yeah, so we're here. Current node is a number, right? So it says if the current value is not equal to nil, and the current value is a type is not equal to an operator node type or a parentheses node type, right? So we allow, it has to be an operator or it has to be a parentheses. Why does it allow a parentheses type though? Oh, I see. It could be like a, so we could have a situation where it's like parentheses, parentheses, right? So we want to make sure that like this, before we hit the parentheses, it's either an operator, it's a parentheses node, or it's the very beginning of the expression, right? Or it's nothing, right? So that's what we're doing here. So somehow this is wrong. Like the current position is wrong when we're parsing open parentheses. So we've hit the operator. So it must be the operator. We're at this point where we hit this operator and we do a rotate left. The rotate left is going to give us a result of times and 15.2, and it should be pointing still at this, right? So that should be fine, but I have a feeling that I've done this wrong. So let's see if this works. Let's see if I can print the node, the current state. No, not. Print something, right? It seems like very strange that it's not printing at all. It might be because this is like an example, and that it's rerouting the output. Because like this node should not actually be there. It's just a placeholder. I see. Let's see. What should I do then to try to debug this? So unexpected parentheses. Let's just return an error with the message that we want. Let's just get it like that. Okay, so here we should get the error that we want. So let's parse, we've got a node value with a type of 0. And the num val is 15.2. Right, so like it's pointing to 15.2 instead of this node here. Which is the problem. Right, upper val is upper val 0. Right, so like it doesn't, it's just, it's yeah, so like it should be returning the full node. Okay, so I did cur.value. Okay, so the value is the node type, this node val, right? And that's 15. 15.2. So it's pointing at the wrong value. I expect it to be pointing to here, and it's pointing here instead. So yeah. So there's something wrong with the let's see. Actually, I think that needs to be like that anyway. So let's see if that's any different. No, we're still. Right, so we're still getting the having the problem. So rotate left should be ending with the current position at the new root node, but it's not. Let's just like panic at p.pause and see what that does. No. Still hits panic unexpected parentheses. So is it like not rotating at all? P.node. What is the current node actually? Right, so like it panics. I've got a current node. Let's do the current node value. Yeah, current node is 15.2, right? Okay. Let's see. So rotate left. So the current value should be right? Like we add 15.2, we're at 15.2. We push this on here, and then we rotate left. And rotate left should leave us with the star asterisk as our current node, but we're at 15.2 for whatever reason. Okay. Let's see if it actually like. Oh, I see. Like if we're adding children, there's no like concept of a left side and a right side for our tree. So we're adding this and like it's going on the left side. That's what I'm doing wrong. So like instead of this type of thing, like here, it's going on this left side. And then I'm calling rotate left and it's doing nothing because there's no right side here. Right, so like I need to have like a nil value or something on this left side. Or something to indicate that this is like actually the right side first. I need to have some sort of like I need to like add this at the second position in the children, or like something similar, something like that. Rather than so like with the operator node, it's always going to have to go on the right side. It always would go on the right side of the number, I think. Or we do this as a rotate right instead. Because like what we could do is have it be 15.2. This gets added on the right side, and then we rotate right, which makes it like this. But if we rotate right, kind of technically this would be on the right side of the end up on the right side. So that doesn't really make any sense, right? Like it should be a proper rotate left operation. Yeah. How do I make this like a thicker thing? Okay. So if I make this like that, does that? No, it doesn't. It's really annoying. Like I want the eraser to erase in black. Or I want to like add a brush. It's black, I guess. And I want it to be very thick. Like how do I make it really thick? I don't know. I don't know how to use paint. Ugh. How do I make it thicker? Oh, what is this? What is this? Oh, is this like my brush thing? Oh, interesting. This is like terrible use of paint here. Just like fill this stuff in. I have no idea what I'm freaking doing. Okay, so alright, so like this stuff, so I need to like maintain some sort of like left and right properly. I can't just like half-ass this. Okay, so I can either like kind of actually do a rotate right, left, or I can do the equivalent operations like, because I know that I'm not actually I don't actually have to do a full rotate left. Like I can actually just swap the two. Like so p.node is going to give me like, so if I say like 15.2 and then I add on this guy, right? Then I just need to swap it so that like it's like this, and then 15.2 is right here. Right? I don't have to like, it's terrible. You get the idea. 15.2 has to be on the left side here. Or like I can just swap it out. Like I don't have to worry really about like there being any children underneath this. Like I can just move this 15.2 to the child of this, and you know, it can be the 0th child of the operator, and I just update the operator's parents to the parent of this one. Right, so like so we create the operator node, and then we just like, instead of rotating, doing an actual full rotate left, we just say like node.parent equals let's see, current is the number, right? So like, so we know the current is the number, and so we want to say like the operator node parents is the current node's parents, right? So this parent here gets moved to there, and the current node becomes a child of the operator node. Right. So parent operator.children equals the children plus the current node, and then the parent is updated, the operator node's parent is updated, and then the current node's parent equals the operator node. Right, so it's something like that. So we do like the equivalent of the rotate left, but we know that there aren't any children of the operator node yet. So if you do that still gives me a parentheses problem. So the current node is also still the number node, so we have to do climb so that the current node is not this node anymore, it's now this node. So we climb up the tree. All right, so we should end up with this structure and we're pointing to the operator node at the end. Does this actually print anything? Or is it going to run forever because I'm dumb? It might be in a fucking infinite loop. No. That stinks. Okay. So it's now looping somehow. Come on, yeah, like these test files are a little bit annoying. These examples are kind of annoying to test because they are printing out data, so you can't like actually print anything. You have to like because it expects it like reroutes the output. So I can't just like print anything directly to the screen. I have to like I have to do something else to like actually debug this. All right. Let's I think I have like a test timeout thing here, so let's do timeout equals 10 seconds. All right. Example calc fails. Oops. But if I do this, oh, interesting. It's not running forever now. All right. So I got 0, but I want something else. I see. So like probably what's happening was that my print node thing was incorrect. It was like looping forever. Interesting. Maybe they were like, the nodes were like self-referential or something. So it's possible that, yeah, like print node was, so this is like self-referential somehow. What did I do? Rotate left, right, so like, okay, so like, yeah. So the problem is that I think that operanode, or the, when I hit the operator, like this number, like numbers basically have to have be leaf nodes. They can't have children, so but the thing is that like the current node could be a parentheses node, like, or it could be which will have children. So I need to remove the operator node from the, I need to pop it off the operator node, the children of the is that right? Or is it len -1? I think it's len if you want to remove one. Right. So it's 5. Zeros, like I think it's -1 actually. I think that would be it. Okay. -15.2. Interesting. Maybe it is like this. I think I'm right. No, it is -1. Yeah, it's going to be empty. Yeah, so this is like problematic. So we get like nil, negative, -15.2. Okay, so -15. So 15.2 is that. So I think it's not an actual minus. It's just a dash that I put in here. So what I should do is just do this, I think. For 0 is less than depth, then print that. Zero is less than depth plus 1. Right? So we're at nil and the 15.2. The problem here is that like the operator is getting removed completely. Something's going wrong here. Because like nil is the root node. So somehow the operator is getting completely lost here. Upper node of parent equals that. Oh, I think because I'm not adding the operator node to the parents, the current node's parents' children. So current parent equals operator node. So I need to remove the current node from the current node's parents' children. So for I of range for parents children, I need to find the parent. Like it should be on the right side always, I think. But that's probably not necessarily true. like if we're hitting an operator like this one here, like the left side could be like a parentheses node, right, where we've added this, and that could be like, some sort of other expression, like 1.8 and 7.9, right? Like it'll be something like this, and then we need to do the rotate. Or no, I guess like if it's like times parentheses, maybe like 15.2 parentheses. So whatever this happens to be, this will have a parent, but it kind of could be the left or the right side. This might be a plus over here, whatever. Like kind of as we're building this out, like it shouldn't be right side ever, but like I think technically I could just remove the last child from the parent, because like the current node should be the last child in the parent, I think. I don't think I need to like look for it in an arbitrary location in the parent's children, but I can't necessarily guarantee that yet. What situations could it be like, like this, where I need to do this rotation here? Like, I don't think there is a situation where that's true, because like this would not be done yet, right? Like we have not gotten to this point yet. Like you wouldn't have parsed out this part yet. So I think this should be like just you have to go up here and update this guy's children. I think it should always be on the right side, but I don't know for sure, because you don't go backwards, right? Like, so I think I can do something like this. Children. Right, you can remove the last child from the parent node. I think that's all you need to do. Right? Slice out balance, range, whatever. Yeah. Yeah, so if it's 0, like, is that something that ever should happen? Like, the current node's children should have been updated, or the current parent node's children should be should have the current node in it. This is a terrible way to debug. Right. So it's definitely a value. It's got something. So if we look at plain error. Type runtime plain error. Maybe because it's a nil value or something. Yeah. So like this is the root, right? But like the root should have children. Maybe there's another bug. No, it's in there. Okay, so it's got a node value, it's got line, column 0, right? So it's like, it's got a child in there that's correct. So how do I remove the value if I don't do it like that? Can I not like set it to like an empty slice? Right, like let's say like x equals 8, right, and x, right, and so like x is like that, right? Like that should be fine. And x minus 1. Yeah, that should work fine. Why does it not work for me? Minus 1. Yeah, like this should never happen, right? Like, this node that I just added should always be in the children, like, the current node should always be in the children of its parent. Yeah, so like it's the root node, but somehow like the children have no have all been removed. Okay. So the other thing I need to do is I've not added the upper node's parent equals the current node's parent, so I remove the current it's the parent. Upper node parent is now parent. It's cur.parent, okay? And then cur.parents I actually need to swap it out. So when this equals upper node. I think that's right. Found parent children. Okay. Plus 1. Oops. Yeah. No. This is minus 1. Alright, there we go. So now we get a tree that is like somewhat close to like maybe what we want, right? So like what we're expecting, I think, in the end is this is terrible. Just go get rid of all this and let's get some black in here. So what we would expect from this is that we have parentheses. We should have at times, right? That right now I don't think we're doing order of operations, right? So we have like 15.2 times, right? And then the right side of this is like the parentheses, and that's 1.8 or plus 1.8 and 7.9. Oh my god, I'm so terrible at this. Right. And then, can I actually go like this? I can. Okay, so this is like left click and right click. Okay, I get it now. So I can right click and erase with the black. That's good. Okay. Alright, so like then, so I got this tree, I think, 15.2, and then the parentheses, and then the parentheses includes the plus, and then 1.8 and 7.9. Okay, so I've got this side, and then that's got a minus, right, as its parent. And on the other side is the slash and 2.5 and 3.0. Okay, so that's pretty close to what I want. Let's see. This order's operations is first. This one's also got what happened first. This one will also happen first. So this is probably the correct order of operations. Though I think that that just happens to be the way that this is the order that these happen. If I change these around, like this is a minus or something, and this is a star or an asterisk, I think the order of operations would be incorrect. We have to work on that. But I think for the most part, we've got the right actual tree being generated now, at least. All right, I think that's where I'm going to leave it for now. I'll probably come back to this at some point. Hopefully that was like somewhat interesting. I think like at some point I've got to get the operations right so that like the multiplication and division operations always happen before the addition and subtraction operations. I think just by nature of the fact that like I've put these parentheses nodes in, that they're always going to get evaluated. Everything inside will be evaluated properly, but these like the multiplication, division, and addition and subtraction, I need to be able to swap them out. Swap the order of operations if they're in the wrong order, which pretty sure I'm not doing yet, but this should work, I think. I think I need to work on this part here. There are also some to-dos left in here. Like I still have not actually implemented the calculator part. Like so, I've implemented the tree itself, or I'm in the middle of implementing the tree itself. But once the tree has been built, I need to actually be able to run it and calculate the number, the result. And yeah, so that's it, I think. And then replace the current node with a new operator node. I think this is done, really. Implement order of operations, that's correct. I still need to do that. Let me move this to do down here. Yeah, so throw if your current value is a number. Right, so like I think we're good here. Current value type equals not equals operator node, and it's not equal parentheses type. Right, so I think that's done. Right, because if it's a number, if the current node is a number, then you will. So okay, so we'll go here. Yeah, so it's just those two to-dos currently outstanding. So basically, next thing I'll have to do is implement these order of operations, and once that's done, I can implement the actual execution of the calendar, the execution of the tree in order to get the value, the resulting value out. All right, cool. I think that's where I'm going to leave it. So I'll come back sometime in the future and finish up the orders operations and then this calculator part. All right, I'm done. See ya.